So we are looking at experiment 7. And in experiment 7, the last part D, is on the 555 timer. So if I scroll all the way down here to 555, let's see, one more. So part D starts on page 11 and then goes into the internal circuitry and the external circuitry that we just talked about. And then we have the equations that we derived. All of that is listed here. And then we have an experiment. So if I zoom in on this, so I'm going to, this is PSpice. So this is PSpice that you can do by yourself, but I'm going to focus on the experiment. So I'm going to come further down here and I'm going to work on building figure D5. Question online is this experiment write-up is due Thursday, correct? That is right. This is due Thursday, the coming Thursday, which should be, what is that, April 9th. Okay, so let's continue. We will do project 3 on Thursday of this week and Monday of next week. And project 3 will be due April 16th, the following Thursday. No problem. Okay, so let's continue discussion on the 555 timer circuit. The circuit diagram is shown over here. It has a chip, an 8-pin chip, 555. So it could be any 555 or LM 555 depending on who manufactured it. But the connections to the pins, one connected to ground. Now if you take a look, and I hope that you guys are able to take a look at my proto board along with the circuit diagram being shown. So pin number 1 is connected to ground, and as you can see, I've put the chip right in the middle of the board in such a way that counterclockwise I have pin number 1, 2, 3, 4, and then 5, 6, 7, 8 on the top. So the bottom leftmost pin here is pin number 1, and that is connected to ground by using that particular pin there, that particular wire there. Pin number 2, based on the circuit diagram, is connected to a 1.8 kilo ohm resistor. Sorry, pin number 2, that's pin number 4. Pin number 4 is connected to 5 volts or VCC. Pin number 4, as you can see, that's the rightmost pin on the bottom here, and using this purple wire we are connecting it to another row here, and then another row over there, and then using that red wire it jumps to plus 5 volts. So purple, red, those are your 3 connections to connect pin number 4 to plus 5. Then pin number 8, well, pin number 8 goes directly to plus 5 volts, so that is connected, that's the leftmost pin on the top here. It's connected to plus 5 volts using that red wire right there. Next, so those are the easy pins. Pin number 1, 8 and 4, those are very straightforward. That's very easy. Pin number 5, which is control, is connected to ground using a small capacitor. In this case it is 0.01 microfarad, which is C2. So I've taken pin 5, rightmost pin on the top, connected it using a 0.01 microfarad, which should have 103 written on it, connected it to that row here, jumped it to that place using the black wire, jumped it to ground rail using that black wire. So that's connected to ground that way. Next, we have 3, which is the output. It's connected to a red LED. So positive terminal, the long lead of the LED is going to pin number 3, and the short lead of the LED is going to a row in which there is a resistor 330 ohms connected to ground on the other side. The 330 ohm resistor is what? Orange, brown. That's the color code of the 330 ohm resistor. So that's the output. Um, so we are left with probably the two complex pins that are left are pin number 2 and pin number 6. And also we have pin number 7 remaining. Pin number 2 and 6 are connected together because they are both monitoring the voltage across the capacitor C1. In this case, C1 is 0.01 microfarad capacitor, which is the orange colored. 104 is the code for that. That's the ceramic capacitor that you see on this. That's the 0.01 micro. That's C1. That's the capacitor that plays a crucial role. And we have been talking about discharging of it and charging of it. It's all for that capacitor right there. So there is that capacitor C1 is connected to pin 2 to ground. So there are two ends. One is connected to pin 2, the other is connected to pin ground. So that's essentially 2, and then the other terminal is ground. And I need 2 and 6 to be connected, so I've used a blue, green. And as you can see, I may be able to zoom in over here. So from pin 2, I have a blue wire, another blue wire there, and a green wire that allows me to connect pin number 2 and 6. Next, we have 6.8K resistor between pin 2 and pin 7. So between pin 2 and pin 7, I have a 6.8K resistor. And that is essentially the resistor that appears right on top of that chip. The color code for 6.8K is blue, gray, red. And on one end it is connecting pin 7, and on the other end it is connecting pin 2. So that's 6.8K. The other resistor in this is between pin 2 and 8 high. So pin 2 is pin 7 and high. So 1.8K resistor is connected to pin 7 on one side and the VCC rail on the other side, which appears right there. So on one side it is pin 7, on the other side it is plus 5 volts right there. So that's 1.8K resistor. The color code is brown, gray, black. Brown, gray, red. What else? I think we talked about all the things. We talked about the two resistors, capacitor, 2 and 6 are connected. Pin number 7 is connected right in the middle of those two resistors, and which is the case because one end of this resistor lies on pin 7. The one end of this resistor, R1, lies on the same pin 7. So that's how we have connected things. Let me quickly zoom out here and see what else we need to do. So if we set up the circuit based on this and only give it a constant voltage using the red wire and a ground terminal. So what I've connected is using the red wire of analog discovery, I've connected the red wire there. And using the black wire from analog discovery, I've connected the black wire there. And if I turn this on, depending on the design equations that we talked about in the previous video, about frequency and duty cycle and how all of those aspects, the on time and the off time, all those parameters of this output square wave relate to the output, right? R1, R2, C1, how do those control the frequency and duty cycle of the output? We talked about that. And in this case, we have R1 set to 1.8K, R2 set to 6.8K, and C1 set to zero point 0.1 microfarad capacitor. So because these are given, we can find out what those expected on time and off time and frequency and duty cycle should be. Right now we are going to use this LED, red LED, to monitor the output. So if I turn on the power supply, so what I'll do is I will make this smaller and I will make this bigger here. And as you can see, I only need the supplies and the scope options. I don't need WaveGen because this is the timer chip itself is my wave generator here. So I'll turn on the supplies. I've set up the red wire to plus 5 volts already. I will turn that on. The moment I turn that on, I hope you saw that the red LED turned on. So if it is on and it is staying on, does that mean that the output is always 1 and it never goes to 0? That's actually not true, because right now what is happening is the red LED is blinking so fast that the human eye cannot see it. We are just seeing a LED that is on, but in fact it is blinking at a very fast rate. So this concept of using this light being on and off is actually used in the current iPhones. I believe iPhone 11 has that technology where the screen brightness is controlled by either having a high duty cycle square wave or a low duty cycle square wave. So if it is on for majority of the time and it is off for less amount of time, that indicates high duty cycle. The brightness of the screen appears high. It's very bright. And if you reduce that duty cycle, you will have a dimmer screen. So that relates to the duty cycle and how it affects the average value of any signal, in this case the brightness. So coming back, so let's see this. So it is actually blinking, and the only way we know that is by applying an oscilloscope probe. So we are by probing that LED voltage across that at that pin 3. So let's do that. We'll try to monitor very important things here. There are two of them. One is the volt. Well, there are three things that are critical. The first one being the voltage across this C1, voltage across this capacitor C1, the charging from 1/3 VCC to 2/3 VCC, and then discharging from 2/3 VCC to 1/3 VCC in an exponential charge and discharge cycles. So that's what we are going to monitor on pin 2, which is the same as pin 6. So I can place a probe. Let's say I place channel 1 on, in this case my pin 2 is very it has a lot of traffic here, so I'll place that on pin 6. That's my orange wire that I've placed on pin 6. That's my voltage across the capacitor C1. I've connected orange stripe to ground externally. So you just using the pinouts of the analog discovery, I've connected orange stripe to ground there. I'm not showing over here to make the circuit look a little bit more clean. Next, I have another channel at my disposal. So I will place channel 2 on, let's start with pin 7, because pin 7 is going to show us when does the capacitor charge and discharge. So let's do this. I have placed channel 1 on pin 6, channel 2 on pin 7, and I'm going to uh, turn on the scope and see if I can measure things. So right now I'm measuring a square wave, but it is not a very good view. So first thing I'll do is turn off noise on both channels and then adjust the offset so that I can see them right in the middle here. And the output also needs to be adjusted. So let's see if I make this -2 volts, it is over there. So perhaps changing the range is a better option. Okay, and then I can use this to trigger, and I only need to see a couple of cycles, no need for all of these. So maybe I can go 500 microseconds per division is probably a good value here. So that's what I end up with. Let me increase the plot width so that is very clearly seen. So on channel 1, I have the voltage across the capacitor, and as you can see, it goes from 1/3 VCC. So in this case, VCC is 5 volts. So it goes from 1/3 VCC to 2/3 VCC. So 5/3 to 10/3. So 1.33 to 3.33. And as you can see here, it goes from 1/3 VCC over here. Oh, 1/3 VCC. Yes. to two third. Hold on. Range for channel 1 is 500. I think I need to have a consistent range here, which is why the problem is. Okay, now they are both 1 volt per division. So now I can see that this particular voltage is 1.33, which is 1/3 of 5, and the high voltage is close to 3.33, which is 2/3 of 5. So that's the orange wire monitoring the voltage across the capacitor. Next, when the capacitor is charging, that means that we are not discharging. So the pin 7 voltage is going to remain high over here. And in later exercises, we will essentially talk about how we can numerically find out the low and the high voltages on pin number 7. So that value here and that value there, we can actually numerically calculate that. I'll show you that in a numerical example later on. But for now, pin 7 is going to read a high voltage when it is not discharging, so when it is charging. And when it is discharging, we said pin 7 connects to ground directly through that transistor, so that's going to read 0 volts there. So that's pin 7 versus pin 6. Next, what we'll do is we will bring in the output of the LED, and LED until now just appears to be on, but if I switch that channel 2 to the output pin, which is pin 3 here, I hope you can see that we are able to generate a square wave where the on time and off time are related to the values chosen for R1, R2, C1, which are in this case 1.8 kilo ohm, 6.8 kilo ohm, and zero point 0.1 microfarad. So that's your pin 3 versus pin 2 and 6. They are both the same. So maybe, I don't know, maybe. Yeah, this is okay. So this shows that it is actually blinking, but I cannot see it just because it is blinking so fast. Now, having talked about these, the write-up asks us to let's see if I minimize this and I maximize this. So you will not be able to see the LED flash. We saw that because it's blinking too fast. I will provide the analog discovery pictures later on. Let's see. Now we slow down the pulses so that we can actually see the LED blink. And there are several ways to slow down the pulses. I can play with R1, R2, C1, multiple values there, and I can achieve a slow square wave at the output of this timer chip so that I can actually visually see the LED blinking. So the task over here is keep R1 the same, R1 and R2 the same, but find a new value of C1 such that the time period of the timer chip is around 1 second. So I did that calculation. So if I show you guys right here, how to calculate. So let's see. I have on time to be 0.693 R1, R2, C1, and off time is 0.693 times R2 C1. We derived these earlier. We need a time period of 1 second, which implies that on time plus off time, I want that to be 1 second. And if I keep R1 and R2 the same, what is the new value of C1? So that implies that 0.693 times R1 plus 2R2 times C1, that is going to be our total time t, I should set that to 1 second. So that if I assume the same value of R1 and same value of R2, which is 1.8K and 6.8K, then C1, the value of the capacitor, should come out to be close to 130, I believe 137 microfarad capacitor. If you use a calculator, you should be able to calculate that out. So clearly, I don't have a 137 microfarad capacitor. So instead, what I'll do is I will try to use two capacitors. One is of value 100 microfarad and the other is of value 47 microfarad. So if I use two capacitors here and I place them, I need them to be added up. So I will place them in parallel. So I will place two parallel capacitors of value 147 and I will remove C1 from the circuit. So I'll remove C1 and I will put two parallel capacitors over there to achieve the slow 1 second square pulse. So let me take a look here. What I'll do is I will leave that over here. I will bring in my circuit. The first thing to prevent anything bad from happening, I will turn off my supply and scope. Next, what I'll do is I will remove the capacitor C1 and then I will have a 47 microfarad capacitor going from, I'm going to use uh, and I have another 100 microfarad capacitor. And I have connected them in parallel. So I hope you are able to see that a little bit. Let's see. Okay. So what I did was I've placed two capacitors. One end is ground, the other end is common. So what I'll do is I'll connect pin 2 to that using a wire. So I'm going to bring in another white wire here. I'm going to connect pin 2 on one end of that white wire and the other end of that white wire will be connected to the capacitors. Both positive terminals, I have connected them to the same point, so that should be okay. Alright, so now on pin 2 I have two parallel capacitors instead of that 0.1 microfarad capacitor. So I've removed that right there. So let's see. If I switch on the power supplies now, what is going to happen? Well, clearly you can see that it is blinking. For a lot of time it is on, for a lot of time it is off, and I am claiming that this is blinking at 1 second, and the only way we figure that out is by looking at the output on and off, the output on the scope. So it seems to me that we are looking at it in terms of microsecond. We are going to have to slow it down. So if I make the 1 second, the time base I changed it to 1 second. So this will give me the clear indication that it is in fact doing the thing that I desired. So by changing just C1, I was able to slow the output of the, because now the charge cycle and the discharge cycle have been slowed down, because as you know, the time constant or the decay constant tau is directly proportional to C, in this case C1. So if C1 goes up, it takes longer to charge up and discharge, and in this case we have managed to get 1 second out of that. So That is your design. Let's see. As a special treat, I have another little circuit over here that I have built based on the same principles of 555 timer. But in this case, I'm looking at the output of output of the 555 timer is being observed by a blinking LED. What if I wanted to hear it? So I'm going to put this by the side, and I'm going to bring in another board which I've used to make a different circuit. So over here I have a 9-volt battery. It is independent of the waveforms here. I have a 9-volt battery. I'm connecting. I've only connected the ground terminal here. I'm going to later on connect the 9-volt input to this top rail a little bit later. The circuitry is exactly the same with only three differences. R1 and R2 have been changed from fixed resistors to photoresistors or light dependent resistors. So the amount of light that those resistors absorb, their resistance is going to change. Just to give you guys a better look at those, I'm going to zoom in there and show you how they look like. So those are the two. Oh, that's the best I can do. Right there. So that's your uh, photoresistor or LDR, light dependent resistor. I'm using two of them for R1 and R2. And for the output, as you can see that black little thing there, that is a buzzer. So I'm using a buzzer for the output instead of the LED. And to protect my buzzer, I have placed a small 100 ohm resistor in along with that. Instead of 330 ohm resistor earlier, I have changed that to a 100 ohm resistor for the buzzer. So those are the three changes that I've made. Changed R1 and R2 to a photoresistor instead of a fixed resistor. So they should respond to the lighting conditions. And I've changed the LED to a buzzer. So as you know, I'm trying to hear a square wave for a particular frequency. So the changes in frequency can be, can be detected by human ear. So let's see what happens if I turn on this circuit. This is going to be slightly uncomfortable. So I would recommend that you lower the volume of your phones, and then selectively, as we move ahead, you can increase it. But right now I'll give you a moment to kind of reduce the volume that you are hearing so that it doesn't make you very uncomfortable. Okay, so I hope you have done that. I'm going to connect the okay. And I hope you guys are able to see or hear the changes in the frequency that you hear as I move my hand up and down. When I give it too much light, that is too much for it to handle. So that's why it's doing that. Actually, if I reduce the darkness, then I'll be able to hear it. Increase the darkness in the room. All right. So that's same principles, same circuitry, output on a buzzer, and input of the a 9-volt battery. So you guys may not have the light dependent resistors to do this at home, but if you can get it, there's a very cool exercise that you can perform. Okay, well, let me check. Were you able to hear that? I am sorry. I'll try to figure out a more pleasant way or a more pleasant sound to do this exercise. But this was sadly one single tone, one particular frequency that it was giving out. Um, okay, that's. Oh, I have one more thing that is left. So the last item on experiment 7 is uh, being able to connect the output of the timer. This is the last one. So the output of the timer, can we use the counter that we built, the 4-bit counter that we had built in part C? Can we use this counter, this 555 timer output to make those LEDs blink? Earlier, we were using a wavegen from Analog Discovery to trigger the counter. Now let's see if we can use this 555 to trigger the counter. So I'm going to bring in two things here. Let me zoom out, bring in my two circuits that I'm going to observe. So one is still going on. So on the left you have the 555 timer. Come on. And on the right you have the 4-bit counter that we had built earlier. And my goal over here is to connect them together and be able to trigger the 4-bit counter using this output from the timer. So for this, all I need to do is take a wire and connect between so I will remove the LED and then take a wire and connect it. I also need plus 5 volts. So I'm going to share the plus 5 volts here, and I also need a ground terminal. So I'm going to connect ground here as well to this board. And as you can see, it has powered on the right. The counter has powered on in a 0110 arbitrary power up state because we didn't use the reset to start it at a 0000. Okay, so I've removed the LED. Now I'm simply going to connect the output of the chip here, which is on pin 3, to the input pin of the NOT gate here. And I hope you guys are able to see that the two things that we built here, 1, 2, 3, 4, and so on. So we are able to generate the square wave or the clock signal using the 1 second time period using a 555 timer on the left, and we are using that timing signal to trigger the counter circuit that we have built on the right. That's part C. This is part D. So that's essentially the last sort of aspect of part D, experiment 7. Okay, so that's all I have for you guys in this. I will stop the recording and take questions.